This is the equivariant cohomology, which is written in terms of x parameters. So I wanted to identify those x parameters in the GKM description, so you restrict to the fixed points. V12, V23, V13, and so using lifting to the moment angle complex, each of these were isomorphic to, it's supposed to be isomorphic to x1, x2, x3, but if you lift the fixed point, there is a, so this vertex is indexed by 1, 2. So on the third component of the moment angle complex, the third torus acts freely. So if you calculate the equivariant cohomology, that equivariant parameter is going to be killed. Yeah? So basically, lifting of this equivariant cohomology to moment angle complex, and then that's going to be in terms of T equivariant cohomology. In that sense, this is going to be isomorphic to x1 and x2. So this one, the first component is going to be killed, so x2 and x3. And this one, the second component, is going to be killed, x1 and x3. But those things are supposed to be isomorphic. Yeah? And I messed up some computation so that I couldn't figure out while I was talking, and I left it there. So let's finish that computation. Okay. So the goal was, when you take x1, in these T equivariant description, it's obvious because these morphisms are pullback of equivariant cohomology. So it's a module homomorphism as a module over polynomial ring. Yeah? So x1 is x1 times 1. So 1 goes to 1, 1, 1. And when you multiply x1, you multiply x1 here, x1 here, x1 here. But then here, x1 is already killed, so it's going to be 0. So here it's x1, 0, and x1, and x2 goes to x2, x2, 0, and x3, and 0, x3, and x3. Yeah, but you're looking at toric manifold. Even though you constructed this toric manifold as a symplectic reduction, so in the beginning you had T action, but in the end you have this R action. So you want to write everything in terms of R, which is U parameter. So I want to translate those X parameters in terms of U's. Yeah. Yeah. So then I wanted to do what happens to these translation. Okay, and I sort of started yesterday. I started to sort of motivate from like very simple things, but then maybe I'll just do really authentic. The truth behind these things, right? So this is a general thing, and it doesn't need to be a toric manifold. Let's just stick to toric manifold. Okay? So forget T and moment angle complex, and so this is a toric manifold coming from some Delzan polytope. And moment map, it's a map from the toric manifold to the d-order Lie algebra of R. Here there is delta. Okay? And the fixed point in this toric manifold corresponds to a vertex which is exactly intersection of exactly n facets. Okay? And in terms of simpliciter complex associated to the polytope, this subset of the index I1 through In is going to be the maximal face of the simpliciter complex. Maximum number of facets that intersect. Yeah? Okay, just for notation. And this computation, right? You sort of take any class here, and then you want to see what happens around the fixed point. So behind this computation, there's this geometry around the fixed point, right? So let's take this fixed point P, or maybe I should say PV, corresponding to V. So the tangent bundle around the fixed point. And from the Professor Lehrman's lecture, there's this local double coordinates, right? And first, the way we do is we apply slice theorem, right? And in this case, it's very trivial because the PV is just a point, which is a single orbit, right? So the normal bundle is just a tangent bundle. So there's a neighborhood of PV, which is isomorphic to an open subset of this tangent space. Yeah? But then, because we have this Hamiltonian torus action, the torus first acts on this tangent space, and it decomposes into irreducible representations. Right? So the notation gets quite messy, but so because I have this I1 through IN, these reducible components is going to be also indexed by those I1 through IK. Yeah, but anyway, so this has, right, so it is a decomposition of the tangent space, okay? And this equivariant double coordinates, it gives you not only the decomposition into the eigenbundle, but also it's compatible with a symplectic structure on the both sides, right? So here it's a complex space, right? And so on the complex space, you have natural U1N action. But when I put this weights here, I have this action of R, right? And by putting this weight means that there is a homomorphism from R to U1, right? Which it's the character, it's given by this character. So it's the n characters, so it's a map from R to U1, there are n of them, right? That defines a map from n-dimensional torus R to standard torus NR. Yeah? So this is the action. The action of R actually goes through this U1N action on the standard complex plane, yeah? And you identify, you have this identification, this and this, right? And then you have this standard symplectic structure here, right? So there's a standard moment map of this standard U1N action. Okay? So what's the moment map of this R on this complex plane, which is just the decomposition, the dual map of this character, right? So, right. So the moment map on this, so this is equal to this direct sum of this weight space. Right? The moment map for this R action on this weight space is going to be composition between the standard moment map and this matrix. Okay? So the equivariant double theorem, or I usually try to find the name local normal form in the literature, and some people also call it this. And this says, this is exactly what Professor Lehrman was lecturing. There is a neighborhood of P, which is U, and there is a local charge into a subset of the tangent space of the manifold, such that the moment map around this neighborhood of the point is given by this moment map. So this composition is written as this way. So this weight is an element of this, right? And this is the standard moment map. Z goes to the norm of Z. Not the norm, but Z goes to the squares. And then you compose with this matrix, you get this. Yeah? It's just that this moment map is somehow centered at the origin, right? But this vertex goes to some random place in this R dual, so I have to shift it. 0. So I think I should say this is P prime, this is PV. So the PV, the moment map image of PV is really the V inside of delta, right? Which is inside of our dual. Okay? And the rest of it is given by this. And this coordinates is this local chart. So you take any points in this neighborhood around this PV, right? And there's a coordinate ZI1 through ZIN, yeah? And the moment map is exactly written this way. Okay, so what does this say? You have this PV in the manifold, and this is the tangent direction, right? And then there are n directions, right? There are n directions. And each one corresponds to this weight space, okay? And under this moment map, it's going to be given by this. Yeah? So each direction, say, let's look at this direction. Right? This direction means that all other coordinates are going to be 0. Right? So they put Zik to be 0, except when k is 1. Right? And then it gives you a ray in the polytope, the edge of the polytope. And the direction is given by this lambda I1. Yeah, lambda I1 is a vector in R dual. It's a weight from the torus R to U1, but also it's a vector in R dual. And it exactly gives you the direction of the edge. Right? That's how you read this local normal form of the moment map. Yeah? So basically the picture is this. So you have a polytope, right? And around this vertex V, you have n edges. And then each generator of the edges are given by the weights of the tangent bundle, the tangent space at a fixed point. Yeah? So, you started with the explicit polytope, right? So you can look at the generating vector of the rays. Yeah? And then also, again, from the Professor Lerman's lecture, those weights must be primitive. And those weights form a basis of the weight lattice. Right? So this set is linearly independent, and those vectors are primitive, and it actually generates whole weight lattice. Right? All right. So the conclusion is weight lambda I k 1 through n at PV are primitive generator of edges coming out of V. Yeah? Okay? So that's the theory behind these local normal form. All right, so let's take a look at a couple of like computational easy facts about these lambdas. Yeah? All right, so let's take a look at this rho I1 through rho IN, right? So those are the normal vector to the facets which defines the vertex. Yeah? And let's calculate the inverse matrix to this. Yeah? What are they? Yeah? I claim that C must be those lambdas. Yeah? I haven't really paying attention to if it's row vector or column vectors. So when I write this horizontal lines, it's a row vectors. Okay? And what do you think? Yeah? So maybe just let's do lambda I1 prime, lambda IN prime, right? So so I call this row, so this is a submatrix of this B matrix, right? B matrix is you put row 1 through row M, right? So it's n by m matrix, but you're picking up just n columns, right? And make it into a square matrix of size n. And it depends on these indices, so let's call this B sigma. Yeah? B sigma are this index set giving you the vertex. Okay? So what does this mean, right? This means that rho ik, lambda ik and rho ik prime, the inner product is plus minus, it's the Kronecker delta. Right? It's equal 1 when k equal k prime, and then if they are different, it must be 0. Right? So that means that if you look at, say, it's really hard to write everything in the board, but just so that a little instructive, right? Yeah. Right, so you have normal vectors here. So this, for example, if you look at this lambda I1, right? The inner product with rho ik, when k is not 1, they're all 0. So that means this vector lies in the edge, which is the intersection of hi's when k, just take out the I1. Right? So this implies that k is in those I1 through IN. You just take out ik part. Right? Because the inner product with lambda ik and rho ik is 1. So just take it out, and it's 0. That means it's in the intersection. Yeah? And plus, the inner product with the same index is 1. Yeah. Okay? And I have to use this prime over here. Right? And I'm claiming that lambda prime is lambda, right? So now we only need to say that when you look at this lambda ik, this has to be 1. Right? I mean, I have to say that I have to show that this lambda ik prime must be primitive vector. Yeah, that's the only thing. Right? But then suppose this is not primitive. Yeah? So the first row of this C is a multiple of something else. But then, the determinant is going to be the multiple of. So if this thing is a times lambda prime, then the determinant of C must be a times a determinant of C prime, where you replace lambda I1 by lambda prime. Yeah? But C is invertible with the Z coefficients, right? Because these form a basis of the rank n lattice. Yeah? So that tells you this lambda I1, all these row vectors must be primitive. Yeah? And we also need to pay attention to which direction it goes, plus minus 1. But then the convexity of the polytope tells you that it goes right direction. Yeah? Okay, so this is some kind of exercise, but that's the idea of how you get this relation. Right? So if you are only given row vectors, not the explicit polytope, and that sometimes happens, right? Somebody gave me a polytope which is given by linear inequalities, and he didn't really give me the picture of it because it was like an 18-dimensional space. Yeah? So in that case, how can I get these edge vectors? You take the vertex and collect the indices, and it's going to be maybe 18 times 18 matrix. Yeah? But then you put it in a computer, calculate the inverse, yeah? And it gives you the generating vector of the edges. Yeah? Most of the example we put in 2-dimensional space or 3-dimensional space so that we can see. In that case, you can just look at the generating vector. Okay, so that's one remark about this weight on the tangent place. It has to do with this generating vector. I mean, it's exactly the generating vector of the edges, and it's given by this inverse matrix of this B sigma. Yeah? So that is actually good, right? Because this C is supposed to be has to do with this transformation between U and X parameters. Yeah? So let's look at this T sigma, which is U1. You put U1 in the sigma component, and the rest of it you just put the trivial group, and it naturally sits inside of a bit T, yeah, m-dimensional torus, right? And then there is this B matrix. Right, these columns are all row vectors. Okay, this composition is given by B sigma. This is something I already explained yesterday, right? Okay, so this means the corollary from that little lemma should be the inverse is C. So maybe I should put the C sigma here, right? C sigma, C sigma, C sigma, C sigma, C sigma, which is given by Okay, so what does this mean, right? We are interested in the weight at the level of the weight lattice, actually do all of that. So here you have U1 through UN, right? The basis of this weight lattice of R, the weight lattice of R, right? And then, so this sequence gives you, say, T sigma dual lattice. Okay? And those are the xi1 through xin parameter. Yeah, I mean you only have the basis elements indexed by elements of sigma. rest of it is already killed, so there's nothing. So that's exactly what I have here, right? So sigma is 1, 2, x3 is gone, right? Okay, of course, this map, so this direction is given by the dual of the composition, right? So B sigma dual. Okay, and so the inverse is going to be C sigma dual. And it's just the matrix, right? So when you send IK, where does it go? It actually goes to lambda IK, the column of the dual of C sigma. Yeah. So I mean, there's a basis description and there's a vector description. So this is a vector, and as a linear combination of the u's, I should write it as lambda IK, and you look at the jth component, you multiply uj. Yeah? J starts from 1 to n, right? As an element of dual of the RZ. Okay, so now I think we can do this, right? So in this polytope, I don't need to calculate the inverse of this B sigma. We already know that this is U1, this is U2, this is minus U1, this is minus U1 plus U2, this is U1 minus U2, this is minus U2. Okay? So here is where I made a mistake in my notes, so I got confused yesterday. But U1, U2, 0. Yeah? And here, 0 minus U1 plus U2, minus U1, U1 minus U2, 0, and minus U2. Okay? And let's just make that kind of computation as a theorem. Huh? I mean, it's a corollary from what I have been saying, right? So under this restricting the fixed points, so for each vertex, you have a polynomial ring. Okay? And where does this xi goes? Yeah? So it goes to a bunch of polynomials, right? For each vertex v. Yeah? So this thing is going to be 0 if I is not in sigma. Right? So this v is V is intersection of hyperplane indexed by sigma. Right? So if I is not in sigma, it's going to be 0. Yeah? Because it's not there, right? It's not there. If I is not in the sigma, then you have to kill that variable in this GChem description. Okay? And then what happens to when I is in sigma, it's going to be in some weights, right? Which is the generator of the primitive vector. So I just say this is primitive generator of the edge coming out of V, and N, not in HI. Yeah. I really know that this is very confusing, but it's just a matter of getting used to this once you want to calculate something explicit. But I thought it's very nice to put this as a statement. Yeah. Okay, great. So this is where I wanted to finish yesterday. So I mean, this is still really algebraic. Yeah. There's nothing geometry, more maybe it's just a little bit of a discrete geometry of the polytope. So now let's do some geometry. So like there are a bunch of classes in this equivalent cohomology which come from the geometry of toric manifold. Yeah? And so the first goal will be, let's look at the submanifold, T-invariant submanifold. And this T-invariant submanifold defines the equivariant class in the equivariant cohomology. And let's see what are the elements corresponding to this submanifold in this GKM description, so that we can identify that class of the submanifold in terms of those x's. Yeah? But before I do computation, this is a general method of constructing equivariant class from a submanifold. Right? So let's consider a more general case, like R acts on M manifold, and there is this submanifold N, and this is our invariant submanifold. And the class is going to have degree in the codimension. So let's take a codimension 2R. Yeah? And I think this method works when you orient the normal bundle. Yeah, because I use a Tomoo isomorphism. Yeah. So in this setup, what you start with is this R equivariant cohomology of N, right? And then there is this Tomoo isomorphism. So Tomoo isomorphism goes to the relative cohomology of the total space of the bundle with respect to the total space minus zero section. And zero section, I just write N sitting inside of this vector bundle. Okay? So there is this Tomoo isomorphism. And then there is this excision, excision of the relative cohomology. And you can actually replace this normal bundle by the whole manifold M, and this difference is just this. And it might be just a small exercise at how you apply excision in this setup. You need to find some set to make this normal bundle to M. And then I'm using this a tubular neighborhood theorem here, right? So the normal bundle sits inside of M. Yeah, I'm using that. And then you can pull back to M. So this, you can think of this as M, and there's an empty subset inside of this difference. So you pull back as a relative cohomology, but this is really a cohomology of M. Yeah? So you have this sequence, and this excision is the isomorphism. And excision is actually given by a pullback, right? Pull. But in this particular case, it's called excision because it's an isomorphism. Yeah? So you have this direction start from here, go over there, and this is a special case of let's call this. So this is a special case of the push forward of cohomology. Yeah, the push forward of a submanifold sitting inside of a bigger manifold. Yeah, push forward can be defined for any the proper map, but here it sits inside of a submanifold, so it's naturally proper, and it has this more geometric interpretation of push forward. without going through Poincare duality.
So M and N are compact or?
So I think this has nothing to do with the compactness, right? Every map can be defined. Well, I'm not sure Tomoo isomorphism, what extent it's defined. Yeah, but there's so many different ways of defining push forward, and this is one way, and this is what we need. And everything is going to be nice in the case of a compact Hamiltonian torus actions. Yeah, every manifold is going to be oriented, and the normal bundle is actually complex vector bundle, so oriented. So everything is just canonically defined. Yeah, but this description is important because of this fact. Yeah. So okay, before that, I have to define this. What's the class for the submanifold, right? You have this, fundamental, the Poincare idea of the right identity elements here, yeah, as a ring. And this is usually, if you have a Poincare duality, it's the Poincare dual of the fundamental class. Yeah. But anyway, so you have one, you just send all the way here. So this is defined. This is the definition of the equivariant class associated to invariant submanifold. Okay. And in algebraic geometry, yeah, people define a class of subvariety. Yeah? And particularly, those things are explained in Fulton's Young tableau in the last appendix. He explains very well about how to define it. So what the problem in algebraic geometry is, most of the time subvariety, you want to allow it to be singular. Yeah? But then if this n is singular submanifolds, I mean singular subvariety, then you don't have this Tomoo isomorphism. So you have to do a lot more to define the class. But in a symplectic category, like most of the time the submanifolds are just smooth, right? So you have a Tomoo isomorphism, and push forward is defined this way. So that's how you define a class. And what the Fulton does in his appendix is so behind this sequence there is so-called Borel-Moore cohomology theory, yeah. And then there's this kind of map to define that you can actually restrict this n to a smooth locus of the subvariety. And then there you have this map. And then he uses, so to define a class of a singular subvariety, you restrict to the smooth locus, and then he has this map, and then that's how you define class of subvariety. But that's a little aside from what we have here, because everything is smooth. Okay? And the fact about this push forward, the relation between push forward and pull back, and push and pull. Yeah? So this is the pullback of this class sitting inside of cohomology of M. Yeah? If you pull back, this is going to be inverse, but it doesn't really matter because it's an isomorphism. And if you pull back over here, it's going to be a Tom class. The Tom class actually sits in here, and then it actually defines Euler class, right? And so if you pull back that class over here, it's going to be a Tom class, and Tom class you pull back by Tom isomorphism, it gives you Euler class. Yes? So in this case, I'm doing equivariantly, so this is equivariant Euler class of the normal bundle. Okay? Okay, so now let's look at the bunch of T-invariant submanifold inside of Toric manifold. And here is the proposition we want to show. Let's let this xi to be the preimage of the moment map of facet. Yeah. So in this case, So facets are all these edges. Yeah? And the preimage of the edges gives you CP1 sitting inside of CP2. Yeah? Those are the T-invariant submanifolds. And you can actually provide lower dimensional faces too. Yeah? So, but this is the only thing we really need to think about. Yeah? Then, I mean, we already know this kind of thing. Yeah? This is xi. So the xi parameter we have been using here are the divisor classes, if you are familiar with the algebraic geometry side. Okay? So as in the class of Stanley-Reisner ring, our equivariant cohomology of a toric manifold. Okay? And proof is very easy, like functoriality of the pullbacks, right? So I already know what corresponds to xi's in this GKM description. Yeah? So we only need to, we want to check, we want to see how this class goes in the GKM description. And then we will see, oh, that we already know. That's x. Yeah? So let's restrict this class, I mean, pull back to the fixed points to PV. Yeah? I mean, V is given by the intersection of hyperplanes, facets indexed by sigma. Okay? All right, so this, the pullback is functorial. So let's just first, okay. So I think I should do first. It's going to be 0. It's going to be 0 if I is not in sigma. Yeah? That's kind of a trivial thing, but you have to think about it a little bit, I think. But I think it's okay. Yeah? Because so here I'm using PV is not in xi if I is not in sigma, right? I mean, I should say maybe that the correspondence in the indices is PV, this vertex, is in this submanifold if and only if I is in sigma. Yeah? So this point is not on this submanifold. If you pull back, it's actually 0. But you have to think a little bit. But maybe I'll just skip that part. And then, so what happens to the rest of the case? Yeah. So now this I is in the index set, which defines the vertex. Yeah? So let's first restrict to xi. Yeah, pull back to the submanifold itself. Yeah, and then restrict to the fixed point. Okay, but this we already know. That's the Euler class of the normal bundle, right? The pulling back to the original submanifold, the class associated to the submanifold actually gives you the Euler class of the normal bundle. So the Euler class, equivariant Euler class, the normal bundle of this xi, restricted to PV. Yeah? So the Euler class is functorial too, I mean natural. So natural with respect to the pullback. So you're taking the equivariant Euler class of the restriction of the normal bundle at the fixed point. Yeah? And this is really representation of the torus R, right? I mean, you have a point and you have a vector space, which is the normal bundle. Yeah? But then, so let's think about this H1 here, right? And then the normal bundle. So the let's look at in this vertex, right? So these vectors are the weights of the representation tangent space. Yeah. So there are two directions at this vertex, right? Two-dimensional, four-dimensional toric manifold. So you have two weight direction, right? And this direction is the tangent direction to this submanifold. Yeah. And the rest of the edges gives you normal direction. Yeah. And we already know the weight of that. That is going to be the primitive generator of the edges, which is not in the facets. So, and this is facets, so there's only one edge not on that facet, right? So this is C of lambda I V. And by definition, the Euler class of this representation, irreducible representation, is exactly lambda I V, the weight. Yeah, the notation this lambda I V is from the corollary I erased from here. So that's the primitive generator, which is not on the primitive generator of the edge, which is not on the facets, HI. So this is exactly coincide with the description of XI and the corollary I erased here. Okay? So great. So that's the proof. Yeah. So you have some class. The first of it is here, right? You have some class, geometric class in the equivalent cohomology. Yeah. And usually it has to do with Euler class or Chern class of of some vector bundle. Yeah. A lot of class can be represented by that, right? And then how do I identify that geometric class in terms of these parameters, right? You already know what happens on the right-hand side. So if you restrict that geometric class to fixed points, and often it turns out to be just a calculation of what the weights of the vector bundle which gives you this class. Yeah, and then compare with this and get the polynomial here, which gives you that geometric class. And that makes it very easy to, it's not really easy, but it's a systematic, algorithmic way of computing what that class is. Okay. All right. So I want to do another example of this kind of identification of some geometric class here, and namely a class associated to the symplectic structure on the toric manifold. Yeah? And how much time you have? 30 minutes? Oh, wonderful. Any questions so far? Okay. So there is this class associated to the symplectic structure on the toric manifold, yeah, and that turns out to be very, very important class in the cohomology. So I'll try to explain what that should be in this Stanley-Reisner ring. Yeah, but before that, let me just define what the class associated with the symplectic structure. So I think I should do, again, R acting on M. Okay. So now the symplectic structure is the main player here. Yeah, and let's say the moment map goes to J of the Lie algebra. Yeah, this setup. Hamiltonian space. Yeah, and so I have this thing in behind, and but the theory is very general. There is this something called Cartan model of equivariant cohomology. So maybe Cartan model of HRM. And what I mean by it's very general is that this happens for any compact Lie group acting on the manifold. Okay, it doesn't need to be Hamiltonian, or it has nothing to do with Hamiltonian action or torus. Yeah? It's completely general. Right? So this is basically, we define equivalent cohomology as whatever singular cohomology, but we define it as the cohomology on the Borel space. The problem of Borel space is it's infinite dimensional. So it's not really easy to think about what the drum cohomology of Borel space. So there is a drum-like model for the equivariant cohomology. And I'll define it here. Yeah, no more than this board. It's very, I'll just give you the definition. Yeah. So the complex, it looks like kind of differential forms. Yeah? We call it our equivariant differential form. And this complex is defined by this way. So this I is just this number to match degrees. So if you take what is n is okay. Yeah. What is the degree n or equivariant differential form? That's going to be elements of this. So symmetric algebra of RZ, the weight lattice. Yeah. So this is basically, the z of u1. No, we are working with now R coefficients. Yeah, because differential form R coefficients, right? So this is just a polynomial ring of R of U1 through UN, yeah, symmetric algebra. I just wanted to use this notation because I want to specify the degree. Yeah, so I could write the degree I, yeah, degree I polynomial. And then you tensor with the honest differential form, drum complex. The index is this, n minus 2i. M. And then there is a natural action of R, and you take an invariant part. No, this is completely general, so you can replace R by G. Yep. Here you have, no, I'm sorry. Sorry, I don't need to put Z here, right? Because we're working with the R coefficients. Yeah, so this is completely general, yeah, for compact Lie groups. Yeah, but I just wanted to do this in a specific case. Right, and so this is the complex, and whatever that is. The differential, of this Cartan model is given by. So you're taking elements from here, say. So this is the polynomial, right? F cross some differential form, beta, and supposed to be R invariant. It's defined as F tensor d beta. Right? So this increase degree by 1, right? And then you do this thing, you add this thing. So this is the sort of equivariant part of this Cartan model. And I have to choose basis in this description. So span, so the dual of the Lie algebra is spanned by U1 through UN, right? And so the Lie algebra, let's say it's spanned by Xi through Xn. Those are the dual bases. Okay, and using that, I should write. So ui is the parameter of this polynomial ring. You multiply ui to the function, and then you tensor with the contraction of a vector field given by the basis. Okay. All right, so the theorem is, the important fact is this actually calculates the equivariant cohomology of M with the R coefficients. Yeah? Okay, with the R coefficients. Okay, and I'm going to stop here. I'm not going to go further into all the property about this Kauta model because I just wanted to make a computation, right? But I put the reference in my lecture notes, so like if you want to learn about these things, there will be very good references, of course. All right, so now we have this setup, yeah? And how can we define equivariant cohomology class of omega? Yeah. So basically, I need to get the closed equivariant form. I mean, yeah, closed form with respect to this differential. Yeah. And somehow the omega doesn't really give you the correct thing immediately. Yeah. But together with the moment map, it defines a nice closed form. So it defines the equivariant class in terms of this Kauta model. Yeah? So before I write this, let's just look at this moment map. Okay? And I want to think of this as an element of this. Yeah? And you can look at this map from M. So, right. So if you put, so this thing, the symmetric algebra of the Lie algebra, which is the polynomial, right? This is a function on R, right? It's a function on R. So you take some Xi as an element of Lie algebra, then by pairing, right, you get a number. Right? So for each Xi, you have a function. Yeah? So that actually says this is an element of R dual cross degree 0 differential form. Yeah, degree 0 differential form is a function. Yeah, and the equivariance of the moment map tells you this is R invariant part of it. Yeah? Okay, so the lemma we can do is if you define omega minus mu R. So what is this? Right? This is going to be sim 0, which is a number. Right? It's just a constant term of the polynomial ring, tensored degree 2 differential form of them. Yeah. Yeah, and this omega is invariant differential form, right? It's invariant under the R action, so that tells you it's in here. Okay, and mu R is in there, and then if you apply this definition, the Kautan differential, it's going to be 0, and write it out, and use the fact that so the Hamiltonian condition is exactly the condition that this becomes 0. Yeah, and it's just a matter of just writing out and see that the omega is closed. Oh, okay, this term is 0, and it's Hamiltonian condition. Oh, this term has to be 0. It's just a computation. All right, so now we have this equivariant class. Right? So the corollary is there is this class sitting inside of R equivariant cohomology of M. Yeah. So I want to know what this is. Yeah. In terms of this, I mean, this is Stanley Reisner ring. If M is toric, right? So I mean, it's a polynomial ring divided by some monomials. Right? It's very explicit polynomial ring. But I haven't really talked about the symplectic structure on the toric manifold, right? So at least let me understand the class, cohomology class of the symplectic structure. Yeah? Because my part was supposed to be cohomology of toric manifold. But still, the toric manifold, symplectic toric manifold, right? We want to understand what the symplectic structure is in terms of cohomology class, which is written very explicitly. Yeah? All right, so the idea is very the same, right? You pull back to the fixed points and see what happens. Yeah? Right. I mean, this is just, you think about this. Yeah? You have this class, and let's restrict it to a fixed point, PV. Yeah? So I haven't really mentioned about all the fundamental properties of this Cartan model. I mean, it's going to be like, what about the functoriality of the cohomology theory? Yeah? And it works all nice that you can pull back those equivariant class to an invariant submanifold too. I mean, especially the fixed points. Right? So what is this, right? You pull back omega to PV. Yeah? If you pull back omega to PV, PV is just a point. And so like higher degree differential form, it's gone, right? There's no like cotangent space. It's trivial. So this term doesn't contribute. Yeah? Here, you're just evaluating the moment map. Right? So the answer is really the image of the fixed points. And this is not only for toric manifold, it's a general thing, right? And we can do all these things. You don't need to assume torus. You just want to have this Hamiltonian compact Lie group action on a manifold, and this is true. Yeah? But in our case, toric manifold, what was the moment map image, right? That's a vertex. Yeah? So the coordinate of the vertex is the GChem description of the symplectic structure on the toric manifold, together with the moment map. Okay? That's very nice, right? It's very explicit. So you don't need to go through this Cartan model anymore. When you look at the polytope, you look at the coordinate of vertex. That's it. Yeah? But okay, let me just now ask. All right. So we already know that this. So basically, so the map pulling back to the fixed point was actually I upper star, right? Pull back by I is the inclusion of the fixed points, right? So if you pull back this equivariant class, that will give you minus UR PV for V vertex, right? So this is an element on this side. Yeah? So I know that this class is equivariant. It's a class in a cohomology. So if you pull back, it's in the image, of course. I mean, it's in the image because it comes from the origin, right? But when you it wasn't very clear, right? Forget the symplectic structure. You look at all the coordinates, yeah? And that gives you a polynomial here, polynomial here, polynomial here. So in this case, what do you have, right? It's 0, right? At this vertex, the coordinate is 0, 0, so it corresponds to a constant 0. And here, the coordinate is 1, 0. So that means this is U1. Yeah? And he, no, this is u1, right? So I mean, this is minus of the coordinates, right? Yeah. So the coordinates of v3 is 1, 0. So 1 corresponds to u1, right, as a vector. And he's v3. So the v13, the coordinate is 0, 1. So u2. Yeah? So how do I know this coordinates, the set of coordinates of the vertex set, is actually in the image of that? Right? It wasn't really clear from the beginning, right? But then, what did I say about which pair, which triple is going to be in the image? That's actually the most important part of the GChem theory, right? It's given by this combinatorial description. The difference is divisible by the weights corresponding to the edge. Yeah? So let's look at this, 0 and u1. So there is an edge here, right? Edge 1, well, this edge is given by, yeah, v12 and v23. The weight is plus minus u1. Yeah? So the difference between this and this is u1. It's divisible by plus minus u1. Yeah? And here, the v13, v12, the difference is u2. The weight corresponding to this edge is u2, plus minus u2, divisible by plus minus u2. And what about this? Right? v13 and v23. So it's going to be u1 minus u2. That's the difference. It's divisible by plus minus u1 minus u2. So without looking at this symplectic structure and calculating the image of that, we already know that the coordinates satisfy GChem condition. So it's an honest class coming from the cohomology class of the toric manifold. And then we just realized that it comes from the class associated with the symplectic structure. Yeah? Isn't that great? Yeah? Okay. But now, so that's what happens in this side. Yeah? But this is like, the tool to identify a class in here. So what is the class corresponding to this symplectic structure in this Stanley-Reisner ring? Yeah, if you are probably familiar with the theory of toric varieties and the divisor classes and the anti-canonical classes and what's the ample divisor embedding toric manifold into projective spaces, you know the answer. Yeah? This formula is hanging around in lecture notes written by Cox. Yeah? Like what is a toric variety, or lecture notes on toric variety. If you start with algebraic geometry, the class I'm going to write down is really there. Yeah? So you can kind of guess and then check it's true, but I wanted to see how that kind of formula comes out from only topology and symplectic geometry. So I struggled a little bit, and I came to realize that. So if you pull back, right, so maybe I should just say, right, so the lemma is, let's look at the vertex, right? So vertex is given by hi1, hin, yeah? And the claim is V is written as minus of mu ik lambda ik d. Yeah? So again, this is the primitive generator of the edge coming out of the vertex V. Yeah? In the corollary I wrote in here. Yeah? And so basically, what does this say, right? What is mu ik? Yeah, sorry, I forgot. So remember, mu's are the important data to define a polytope, right? Polytope is defined by this linear inequalities. Yeah. Okay, this eta I. Yeah. So V is given by those facets. Yeah, I1 through IN. Okay, so for each facet you have this eta value, and you multiply that to the generating vector corresponding to. So this, again, this is an edge coming out of V, which doesn't lie on the facets HIK. Yeah, so it paired with the facets, even though it's not on that facet. Yeah, and how do I show this? Right? The vertex is, it's kind of amazing formula if you just sort of find out on your own, right? So let's see. This one, U is 1 0 0 and 1. Yeah, remember this polytope is given by this inequality. So the eta value is 0 0 1. Yeah. So this is indexed by 1. This is mu. Oh, eta. Right. Why am I writing mu? Mu and eta looks similar. Yeah, eta value. Yeah. So let's see. V12 is going to be. So you have the eta value is both 0, right? Eta 1b 12 plus 0 2b. So it's anyway 0. Yeah. The coordinate of v12 is 0, and v23 is v23 0 and 1, and v23 you have an edge minus u1 plus minus u1 plus u2. So it's not really agreeing. Yeah? All right, so let's just forget this computation and then see what's happening in this proof, right? Okay. So what defines this lambda IKV, right? So it was the inverse of this, the submatrix B sigma, right? So it had this relation, right? For a given vertex, which is the intersection of these facets. The definition, I mean, the way you can compute by linear algebra or this generating vector of the edges, it satisfies this equation. Yeah. So V of IK, what is this? V of rho IK is going to be, right? So you are, maybe I'll put the K prime, right? You're taking the inner product this and this, yeah? And when K and K prime, they don't agree, the inner product equals 0. But then if it agrees, it's 1. So you multiply eta and then take minus. So it actually pulls out this minus eta ik. Yeah. So this means, yeah, V satisfies this. Yeah, for any k prime 1 through n. Yeah. So the vertex satisfies, you know, it lies on the hyperplane given by those hi1, hin. The hyperplane is given by this equality. So the V satisfies, V lies on this intersection. But then there's nothing else, right? So that's the only one, unique one given by this. I don't care about other inequalities. It's supposed to be satisfying other inequality too, once it satisfies this equation. Yeah? So it uniquely gives you the solution to these equations that gives you the vertex. So that means this is it. Yeah? So every time I try to do some computation that I haven't done last night will be messed up, so I'll stop. I will just make it an exercise to work it out to make sure that that lemma is correct for this thing. Yeah? Okay, so that tells you when you pull back, the class of the symplectic structure, that gives you the minus the vertex, right? So for each PV, you have minus mu r PV, which is the minus of the coordinate of the vertex, but the coordinate of the vertex is given by this minus of I, right? Plus. Okay? But then, this is actually mu ik so this is actually I starts from 1 to m of mu ik of pullback of xi. Oh, sorry. Yeah, it's not, this step is not really immediate, but this is how things works nicely in those kind of computations. Yeah. So let's see, right? So what is this? So this implies that this omega mu r is equal to the sum mu I xi. Okay, so this is the last conclusion I can make today. Yeah. The class associated with the symplectic structure, you sum all these xi parameters with the weight of this not mu, sorry. I've been writing mu's instead of eta. Yeah. So you weigh each parameter by eta I, which gives you a class in the Stanley-Reisner ring. Yeah? And let's see, that I think I can check. So 0 times xi, x1, plus 0 times x2, plus 1 times x3. Yeah? Where does this go? Yeah? x1 is gone, x2 is gone, x3. Yeah? Yeah, so x3 is x3 is 0 minus u1 minus u2, right? So this is minus of 0, 0, and u1, 1, 0, 0, 1. Yes. Right? So this is v1 coordinates, 0, 0. This is v1, v1, 2, right? v2, 3 is 1, 0, the coordinates of the vertex. And this is 0, 1, the top vertex. Yeah? You take a minus. That is the image of this. So this, we already know that image of the symplectic structure, right? Yeah? Yeah? So it's kind of, if you don't know the symplectic structure, the class associated with it, you just calculate, you take out those numbers and you multiply the x variables and then you send it by this map, or you get the vertices, y. Yeah? But it actually comes from this Kautan model, how to define equivalent cohomology class for the symplectic structures. I think we ran out of time. Thank you very much.